Welcome, Math 13 students. Today I have our lecture on section 4.1, probability basics. So I'm going to start with the notion of a claim. This is something that we'll have to deal with as we go further on, especially into our inferential statistics. So here's a claim. My study method will increase your test scores. Now, the notion of probability measures the chance of that claim being correct. And we need to develop methods of assessing these types of claims, claims that might or might not be true, might or might not be true for everyone. So this notion of probability is very, very important. Probability is the chance something might happen. It's only in play while your coin is flipping through the air, so to speak. Once your coin lands, the notion of probability has no more meaning. All right, and before I go on, I will note that this notion of probability is a brand new concept for the vast majority of my students. It's something that is mathematical in some sense, but it's also a very intimate and personal topic. We don't have a lot of experience with it in the math realm, but we're all used to what happens when we take a chance and it doesn't turn out okay. So with that said, let me go on. Some vocabulary. All right, so we have the notion of an event. Now, I'll be providing an example or two as we go through this, but an event is any collection of outcomes from some sort of procedure. For example, I might flip a coin, and when I flip a coin, that is my procedure. If I record the result of that coin flip, those are my outcomes. Now, there's different types of events. Basically, we like the notion of what we call a simple event, and that is an outcome that cannot be further reduced. I'll give you examples. Finally, if we take all of the simple events from some sort of given procedure, what we'll end up with is something called the sample space. This is the list of all simple events from a procedure. Let me give you an example or two. Now, we use these examples throughout the chapter 4 material, so students really should commit them to memory, or at the very least have access to them and know how to use them. Now, suppose we flip a coin once. We're going to assume that our coins are fair and everything works fine. So if I flip my coin once and I record the possible outcomes are either a head or a tail. Both of these outcomes are simple events. The notion of a tail or a head on your coin when it lands really can't be broken down any further. But there is subtlety here. This time, in the next example, we're going to flip our coin 3 times. Now, if I flip my coin 3 times, what is the possible list of outcomes that I might see? And I've got to get all of them in there. I might have 3 heads in a row. The first 2 might be heads, and the third might be a tail. Maybe the middle flip is the tail, and the first and the last are heads. Maybe my first flip is a tail, and the last 2 flips are heads. I also need to consider the possibility that I get 2 tails and 1 head in my 3 flips. 2 tails, 1 head, 2 tails, 1 head, 2 tails, 1 head. And you can see that those give all the possible arrangements that might happen there. Finally, TTT is a possibility that I get 3 tails in a row. This is my sample space. And all of those guys in there are simple events. Now, Consider this event. The event that I am interested in is the event where I see two tails in those three flips. The two tails in three flips are covered by those three simple, simple events. So the event of two tails has actually built within it simple events. Now, let me share some notation. For our notation, we usually like capital letters like A, B, and C. For probabilities, we write P with the A in parentheses. This is very much P of A. Why do I say P of A? Because P of A is our function notation, and this is our function notation. The function returns a probability and takes as an input an event. So P of A is the probability event A will occur. Now, a little bit about our probabilities. All of these probabilities, whatever they might be, fall between 0 and 1 inclusive. It means my probability could be 0 perhaps, it could be 1 perhaps, or it could be anything in this interval between 0 and 1. I will note that if P is equal to 0, P of A, excuse me, is equal to 0, then A will not occur. On the other hand, if we know that the probability of A is equal to 1, then event A must occur. In between, the chance becomes less as we get towards 0, it becomes more as we get towards 1. So there's my notation. Now, let's talk a little bit about calculating probabilities. There are a couple of different approaches to calculating probabilities depending on the context and the type of data that we might have. I'll begin with what we call the relative frequency approximation of probability. Basically, we observe a procedure. We count the number of times a given event A might occur, and then we make a fraction. The probability of A will be simply the number of times A occurs divided by the time the procedure is repeated. Let me give you an example involving some real-world situations. Suppose a biology experiment has grown some peas. We have a total of 680 peas. Some are green, some are yellow. 148 are green, 152 are yellow. We're going to randomly select one of these peas, and we want to find the probability that it is yellow. What is the probability that the pea is yellow? So, by my relative frequency approach, I've got my event, and I'm not going to call it A, I'm going to call my event Y. Why? Because we're looking at yellow peas, not green peas, not any other color of peas. Make the notation work for you. So we count the number of times we see the yellow peas. How many times do we see yellow peas? We see yellow peas 152 out of a total of 680 observations. So the probability of a yellow pea being pulled from this group is 152 divided by 60, 680. I dump that into my calculator and I'm going to round that to 3 decimal places. There is a very precise rounding rule, but I will go over that at the very end of my discussion today. Now, I'm going to give you another example of the relative frequency approach, and I want to introduce some more vocabulary. We have the vocabulary of what happens when we give a test and we observe results. Very timely in this COVID era. So we have the notion of what we call a false negative. A false negative, we have an incorrect negative test result. It's really positive. So the test says you have no COVID, but you have it anyway. That's an example of a false negative. False negative has a fraternal twin, and that is a false positive. So an incorrect positive test on a result. Well, maybe that test says that you're pregnant, but you're really not. That's an example of a false positive. So let me run through an example involving both the relative frequency approach and this notion of false positives and false negatives. So, drug screening in the workplace, it does happen. Maybe where you work, you are required to test for illegal drug use. Maybe you're not. But we're going to randomly select one person from this group of people. So we went into a business and we took a bunch of tests. Some people used drugs, some people did not. Some people test positive, some people test negative. So I will note that if you used drugs in the workplace and you tested negative, that right there is the false negative. Maybe you didn't use drugs, but the test came back, yeah, you did. We think you used some drugs. 25 people did not use drugs and yet tested positive. That is our false positive. So I'm going to answer the question, find the probability of a false positive. I've identified that there are 25 false positives in this entire table. However, I need to do a couple of other things. I really need to find row totals and column totals. If I add the columns up, they should get to 555. If I add the rows up, they should also get there. So there were a total of 555 tests given. 25 of them were false positives. So the probability of a false positive, note my notation. This is designed to help us understand what's being asked. We have 25 over 555. That's a simple calculator problem. And I get a 0.0450. I'll talk about why I write that the way I do at the end of this presentation. We will go over rounding. So the probability of a false positive, 0.0450. About 4.5 times out of 100 tests will come back with a false positive. So that's a couple of examples of the relative frequency method of approximating probabilities. Now I'm going to look at the classical approach. So our classical approach to probability is another approach that I use from time to time. And again, these approaches that we use really depend on the type of problem and the data that we are given. Furthermore, when I use this notion of classical approach to probabilities, it requires that we have equally likely outcomes. And this is an important component. If we don't have equally likely outcomes, my discussion really will not apply. That's a more advanced type of question, basically. Something that is an example of equally likely outcomes, a coin flip. Same chance it'll come up heads versus tails. Maybe a birth, boys versus girls. And I'm sure there's other out there, true versus false on a quiz. But basically, if a procedure has n different, this is important, we have n different simple events, all equally likely. And we know that our event A occurs S ways, then the probability of A is literally the way that A occurs divided by the number of simple events. Using my notation, it's S over N. Although I don't really use that notation an awful lot, you'll see as I go through this example. So we're going to flip a fair coin 3 times, and we're going to answer 2 questions. The first question, we're going to find the probability of exactly 2 heads. There we go. Probability of exactly 2 heads. That's the first question. So my sample space for flipping my fair coin 3 times. I've already gone over it, but here we have it again. We use this a lot. So have it handy for answering these types of questions. So if we're looking for 2 heads, where are the outcomes that have exactly 2 heads? There they are right there. Those are the outcomes where we have exactly 2 heads. So this is 3 divided by 8, the total number of objects in our sample space. These are all simple events in there again. 3 divided by 8, 0.375 is 3 divided by 8. Take a look at the next one. The next one. We want to find the probability of, this one's different, at least 1 tail. So we want the outcomes that have at least 1 tail. That means 1 tail, 2 tails, or maybe even 3 tails. If I take a look at my data set, the outcomes that have at least 1 tail are right there. Those are the outcomes with at least 1 tail. That is 7 out of 8. 7 out of 8, 0.875. So you can see that the work is not particularly difficult mathematically. It's essentially counting and making a fraction. However, the setup and the interpretation is actually quite advanced. You haven't done this before. So it takes a while for this to sink in. Now, we have one last type of probability, and I'll spend very, very little time on this. And it's called subjective probability. Subjective probability. You guess using your own life experiences. Basically, you do what? Guess. I think the book says estimate, but they're really just being kind. You're guessing. So this is what you do essentially when you see that train coming and you're sure you can make it across those tracks. You've done it before. And so you gun the car, you try to make it across the tracks, and well, maybe you do, maybe you don't. That's the notion of subjective probability. Now, the last thing I need to do in terms of combining these various types of ways of calculating probability is to sort of try to link them up. We have what we call the law of large numbers. And this is a very important rule, but it's super subtle, and honestly, the basics of it require some very advanced calculus. We can still appreciate it, though. The law of large numbers says that as a procedure is repeated again and again, the relative probabilities approach actual probabilities. So for example, if we flip a coin over and over, the number of heads divided by the number of flips will approach 1/2. 1 out of 2 or 1, 0.5. This is what we mean by the law of large numbers. It does link the two types of probability eventually, but you essentially have to repeat your procedure essentially an infinite number of times. Don't stress about that. That's calculus, not this. So the law of large numbers is our link. Now I have one more thing to define, and then we can go ahead and I'll show you about the rounding. We have what we call the complement of an event A. The complement of an event A consists of all outcomes where A does not occur. Here's an example. We have 3 million skydiving jumps on record. There were a total of 21 fatalities in those 3 million jumps. Seems safe to jump out of a plane, you know? So we want to find the probability of not dying. I mean, really, that's what we're interested in if we do take this skydiving course I'm thinking about. So the probability of not dying means we have to look at all the outcomes minus those that died. So 3 million minus the 21 poor souls that didn't make it to the ground alive, although I bet they did make it to the ground. 2,999,979 people actually jumped and lived. And we'll divide that by all the jumps we have on record, the 3 million, and we've got our probability for the complementary event. So we have special notation. A and A bar is the complement, as we like to call it. Put the bar over the top, A bar. All right. So that pretty much runs me through the detail of the chapter 4.1 material. There's a lot in there. There's a lot of different threads that we will pull on over the next several sections and chapters. But let me talk a little bit about rounding probabilities first. When we round probabilities, the rule we adopt for our class is that we round to, look at what this says, 3 significant digits. Notice, this is not the same thing as 3 decimal places. So I'll need to tell you exactly what we mean by 3 significant digits. And for our course, here's how we go about it. We're going to go to the first non-zero digit. We're going to take 3 digits. And then we look at the fourth to tell us what to do with the third. And this will give us our rounding. Huh? I understand. Let me give you an example or two. All right, so we've been working with fractions. We'll continue to do so. So suppose our probability requires we calculate a 2 divided by 147. So I plug that into my calculator and I see what I see right there. So what I need to do is I need to round to 3 significant digits. I go to the first non-zero digit and then I look, I take the 3 there and then I look at that fourth to tell me what to do with the third. And since the fourth digit is 4 or less, I keep the 6, and this is 0.0136. Oh, this is wrong. You see that right away. So let me go ahead and take 3 divided by 1,584. Excuse me, that's 3 divided by 1,587. And I get a 0.001890 and a 3592. So 3 significant digits. We go to the first non-zero digit. I take 3. And I look at the fourth to tell me what to do with the fifth. So 0.00189 is my value rounded to 3 significant digits. Now, there are times where my students will come up with numbers that are very, 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 very small, very close to 1 for a probability, excuse me, very close to 0 for a probability. And this does bother my students quite a bit. You're going to see me do this plenty of times on screen, and I'll save a little bit of it for then. But right now, if I take 7 and I divide it by 10,398,142, this is what my calculator shows me. And this is my calculator doing scientific notation. So 6.73197 and change. I see the little e and the -7. That's my scientific notation. So 10 to the -7. Remember what that means. It means I have to take that decimal place and move it out that way 7 places. So there's 1, 2, 3, 4, 5, 6, 7. And then I have to take 3 significant digits and look at the fourth one to tell me what to do with the third of the 3 significant digits. I'll keep the 3 because the one says so. And I get a 0.000000673. I cannot tell you how much we do not like all those zeros. That's true amateur hour. No, we like our scientific notation. Truth of the matter is, once I've got my scientific notation here, I really want to stick with it, because I can use my 3 significant digits right here. In fact, the first number I see is the first significant digit. And I just take the first 3 digits. The fourth tells me what to do with the third. And then that's my rounding. And I make sure I write it as 10 to the -7th. By the way, this is what you will see as a solution or a result on a quiz, an exam, or perhaps in your textbook. Rarely do we see a whole bunch of zeros like that. We just don't like them. They're hard to read. So there we go. There's your introduction to probability. It'll post on the Canvas website probably in the next couple hours. Thank you and good night.